So let's talk about the first learning objective for Unit 1. Recognize soil fertility issues within the many factors affecting crop productivity. So let's talk about this specifically. Let's take a look at historical crop yields. And this figure is a little outdated. It goes to maybe about 2010, but it tells you a very good story. It tells you a story of corn, wheat, or cotton yields with respect to year. And what do you see? You see right around roughly 1945, 1940-ish, an upturn in crop yields, specifically with corn, wheat, and cotton. Here's corn in the open circles. Here's wheat in the closed, oh, I'm sorry, here's wheat in the triangles, and then here's cotton in the closed circles. Why do we see an uptick? We see an uptick in the 40s due to a number of processes that were utilized during the Second World War that were applied directly to the fertilizer industry and the creation of synthetic fertilizers. And this is where we saw a major uptick and where we see a major uptick even to this day. So if you look at fertilizer use, okay, so there's two graphs here. At the top graph is fertilizer use in the United States, and the bottom graph is fertilizer use worldwide. And we're looking at three of the major macronutrients: nitrogen, phosphorus, and it says potash, which is potassium. Okay, so phosphate or potassium. And what do we see? We see a strong uptick from, actually the uptick likely started where you can't really see it on this graph, but back in the 40s. And it continues today. And what these two graphs tell you is that nitrogen is king. And worldwide, we recognize that nitrogen is king and oftentimes the most limiting nutrient in terms of crop growth or plant growth, and thus the greatest use in terms of fertilizers is nitrogen, both within the US and globally. Now, these figures actually relate to something that's called nitrogen use efficiency, which I'm going to share with you on the next graph. So this graph is a graph of nitrogen, or I'm sorry, it's nutrient use efficiency. And what you see is on the x-axis, years, much like on the previous graph. And on the y-axis is kilograms of grain per kilogram of fertilizer, be it nitrogen, phosphorus, or potassium. And what we see is that with phosphate or potash, phosphorus or potassium fertilizers, we actually do within the United States a fairly decent job of getting a return on fertilizer investment for phosphorus or potassium. So what this graph tells you is that over time, we've been able to increase the kilograms of grain per kilogram of either phosphorus fertilizer or potassium fertilizer added. We do a very good job of this. Okay, it's not perfect, it's not 100%, but we do a much better job of utilizing phosphorus and potassium as compared to nitrogen. Here is nitrogen use efficiency over time, and it's not quite flatline, but it's pretty close to being flatline. And that's because the values are all over the place. Because in soils, nitrogen is simply a leaky system. It ends up going everywhere you don't want it to go. It leaches, it volatilizes, and it becomes a gaseous phase under conditions that are anaerobic. And the use efficiency is relatively low. And so you may have heard of some products like slow release products or control release products that are additives to fertilizers or fertilizers themselves that are geared towards improving nitrogen use efficiency. And some work pretty well and some don't. It depends on climatic conditions. And we're going to learn about this in this class. So let's talk about potential crop yield, because we've just talked about crops. And the theoretical possible yield based on everything being optimal in a condition is listed here, right? For corn, soybean, and winter wheat. So currently this is pretty current. The mean yield 2 years ago for corn, soybean, and winter wheat was 171, 51, and 50 bushels per acre. The potential crop yield, however, is about 600, 250, and 300 bushels per acre for each one of these crops, respectively. So if you think about this, why in the world do we see such a dramatic shortfall for potential crop yield versus actual crop yield? And you probably would realize that it's based on a number of factors like climatic factors, soil factors, crop factors, human-induced factors, etc. And so if you think about what we can do, what you're going to learn in this class are ways to at least overcome some of these discrepancies between potential and realized crop yields. And soil fertility management addresses these yield differentials. So there's a table in your notes. If you have your notes open on your laptop or have them printed out, there's a table that looks much like what you see on the screen. And it looks just like this. And we're going to fill in this table. And what I'd like you to do is, I'm not going to fill in the table completely for you here. We'll discuss some of these factors. And what I'd like you to do is fill in the table with other factors that we haven't discussed. And I want you to do this for a reason, for those students that are online. And the reason is because you likely may see something like this on an exam. And you'll have to regurgitate what are the climatic, soil, and crop factors, and potentially other factors that may affect that difference. So let's talk about climatic factors. And some of these are no-brainers, especially if you work in any industry that works with plants outside under essentially uncontrolled conditions. Temperature. It's too hot. It's too cold. Precipitation. It's too wet. It's too dry. Wind. It's too windy. It's blowing away soil. It's eroding soil. Not enough sunlight, right? So not enough growing degree days for a plant, etc. You could keep going. A tornado hit a town. A hurricane hit a town. This happened to one of my colleagues in Florida. The 3-year study, 1 year was completely lost due to a hurricane that flooded the fields that she was working in. Go figure. These things happen. Or like in the Midwest, several years ago in Iowa, torrential downpours for early in the season. Producers couldn't get into the fields to plant their crops, and thus crop yields suffered subsequently. Soil factors. Soil is too coarse, doesn't hold water, doesn't hold nutrients. The soil is too fine, it's too clay. It holds water tightly, and the system is saturated. There's not enough nutrients in the soil. We've mined nutrients out of the soil over decades of crop growth, and we haven't added those back. What else? Soil contains concentrations of heavy metals that are detrimental to plant growth. Soil is too salty, etc. Crop factors. You chose corn, but you chose the wrong variety of corn for your location, and it grows poorly. Right? So there's some genetic factors that are involved. The leaves on the corn plant aren't at the perfect angle or optimal angle to collect sunlight for photosynthesis. You can think of, I think, many other crop factors. And I want you to fill in this table with other factors that you can think of. And should we add a fourth factor? I think we should add a fourth factor. The fourth factor is human. And we do a pretty good job of manipulating systems or ecosystems or agroecosystems. And sometimes we make oopses. What if you started tilling your soil and your implement broke down in the field and you couldn't get back to it for a couple of weeks and you couldn't plant? Or you over applied a fertilizer to a parcel of ground and you killed your crops. Or you inadvertently applied a liquid manure effluent to a system, not realizing that it had either too much salt in it, or too much copper in it, or too much of another nutrient in it, or lack of a nutrient, and it caused detrimental effects to your crop. So, with that said, what are the primary soil-related yield reducing stresses worldwide? There are three. Moisture-related stress. It is simply too dry. This is prevalent in the Western United States currently. Temperature stress. It is way too hot early in the season, which is something that we often see in the Western United States, or it's too cool early in the season and the crops don't emerge quickly, like we see sometimes in the Midwest or upper Midwest. And the third related soil response for yield reducing stresses is nutrient related stresses. We simply don't have optimal nutrients present in our soils to meet the demands of a growing crop.